let's go over a proof of the non-planarity of K5, that is the non-planarity of the complete graph on 5 vertices. We'll start with the definition of planarity, as well as the definition of what a planar embedding is, and then we'll go through a few essential points that should be made before we begin the proof. So let's start with the definition. So we say a graph is said to be planar if it can be drawn on the plane with no edge crossings. So if you have a graph, you start with a graph, we call it a planar graph if you have, or if it's possible for that graph to be drawn on the plane, usually, or typically we think of the plane as R2. So if that can be drawn with no edge crossings. There's a minor exception made here. So the only places where edges can cross, in a sense, or where edges can intersect, is at end vertices only. So I'll just make that point clear. That is, edges intersect at end vertices only. So when you have such a representation or such a drawing, we call that drawing, where you have no edge crossings for the graph, we call that drawing a planar embedding. So such a drawing is called planar embedding of the graph. So we have two definitions here that I've underlined. So I want to make that clear that a planar embedding is different to a graph being planar, because the planar embedding is simply a drawing of a planar graph, where you have no edge crossings in that planar embedding. So let's just go through an example. We have here the complete graph on 4 vertices. So say we have 4 vertices scattered in this way. And because we have a complete graph, every pair of vertices are adjacent. So there's an edge between every pair of vertices. So let's draw that out. So they're not all yet connected. Now they are. Right, so if you pick any random pair of vertices here, I should make these vertices a lot clearer. Pick any random pair of vertices, you can find an edge between them. Right? The problem with this graph drawing here is that it is not a planar embedding, because you could see here, at this point, we have an edge crossing. So can we draw this, the complete graph on 4 vertices without an edge crossing? So you could try it on your own, see if you can. It's actually not too difficult to kind of manipulate how you should draw the vertices and how you should connect the vertices with edges. So I could change this a bit so that I can draw it kind of like this way. Should have drawn the vertices first, but it doesn't matter. So here we have 4 vertices. They're not all yet connected to each other. What I can do is draw an edge between this vertex and this vertex, another one like that, and then another one like this. So now we have every pair of vertices in this graph having an edge between them. So as you can see, there are no edge crossings. So another, I guess, more elegant way you could draw it is like this. So you form a triangle. Then connect the vertices like this. And clearly there are no edge crossings except at the end vertices. So we call these 2 graphs here a planar embedding of K4. So that's one example. Now, the point of doing this is to motivate the non-planarity of K5. So what is K5? So it's the complete graph on 5 vertices. So let's just have a look at this. We want to add an additional vertex. The classic way to draw K5 is kind of like a star shape. And it's not yet complete. Let's create a cycle on the outside here. And as you can see, it's obviously not a planar embedding because we have some edge crossings. So I want to make that clear, is K5 is not a planar embedding. The question is, does a planar embedding exist? So what you can do is rearrange the vertices and edges as you like and try it for yourself. You'll find that such a task is impossible. But let's just give it one attempt here. So I guess what I can do is arrange these 5 vertices like this. So let's say we have a cycle here between around these 3 vertices, and then we still have to connect a lot more vertices here. So what I can do is connect those 2 vertices like that. I can connect that. I can connect this vertex here to this vertex here. Likewise with this one here. And now I'm left to connect this vertex with this one, as well as a couple other ones. So let's try doing that. So each vertex should have degree 4. That is, each vertex should have 4 edges incident with the vertex. So we still have to deal with this one. We need to connect it to this vertex here. As you can see, based off how I've drawn this graph here, it's kind of blocked off. it would seem that you have to cross that edge here to get to the other vertex. So I've already failed. This is a failure, which is a good thing because it's necessarily a failure. So the question is, does a planar embedding exist? The answer is no, no planar embedding exists, and we want to prove that. There's a few other points that should be made before we go through with the proof that I'm about to present. There's a theorem that is used in the proof that I'm going to do. The theorem is the Jordan curve theorem. Oop. So I'm not going to be too rigorous here. I'm just going to present it in an informal way, just so that I can use it when the proof asks for it. So a few points. I'll just, I guess, say them verbally. So we have that a curve is, so this is not yet the theorem. So a curve is a continuous image of a closed unit line segment. So it's probably what you think it is. It's a curve. That's a curve. This is a curve. And that's, I guess, the definition of what a curve is. It's a continuous image of a closed unit line segment. Now, a closed curve is a continuous image of a circle. So you can imagine that when you have a curve, you close it off, then you have what we call a continuous image of a circle. So it's closed off. So we can call this C, for example. Now, a subset of the plane is what we call, before we get to what arcwise connected means, we want to know what a simple curve looks like. So a curve or a closed curve is simple if it does not intersect itself. So this is a simple curve. Now this is a simple closed curve. But this is not simple because you have, or it intersects itself at that point. Now, a subset of the plane is what we call, is arcwise connected if any two of its points can be connected by a curve lying entirely within the subset. So you have some subset of the plane. We call this subset arcwise connected if you have any 2 points and you could connect them with some curve that lies entirely within this subset here. And clearly this region that I've drawn is arcwise connected. It's not so clear, you might be on the boundary there, it might be a bit interesting, but that's the main point. Now, the theorem says that any simple closed curve C, let's call it C, in the plane, so that partitions the rest of the plane into 2 disjoint arcwise connected open sets. So that's the statement of the Jordan curve theorem. So yeah, I guess this theorem can be applied in many different branches of mathematics. And my presentation here is clearly just a very elementary presentation. So it's not too important to go through all the rigorous details, especially, nor is it important to go through a rigorous proof of the Jordan curve theorem. It's seriously non-trivial. So here's the statement of the theorem. So if you have a simple closed curve C, this is lying in the plane, we say it partitions the rest of the plane. So by the rest, we mean not part of this curve C. So here you have one arcwise connected open set. Here, the rest of the plane is another arcwise connected open set. So we have two disjoint arcwise connected open sets that is separated by the simple closed curve C in the plane. So interestingly, a proof of the Jordan curve theorem, you'd think, it makes sense, right? You have a curve, there's this bit, and that's the entire plane. But to prove this is actually quite difficult, and there's supposedly a proof of this theorem that relied on the nonplanarity of the complete graph, complete bipartite graph on three vertices. And that was actually proven in 1992, so not too, it was quite recent actually. And interestingly, we're going to use it, the theorem, to prove the nonplanarity of K5. So I did mention the complete bipartite graph on three vertices. So if you don't know what that is, it's a complete bipartite graph on three vertices. You have a bipartition, say this group and this group, where every vertex in one set is adjacent to every vertex in the other set, and no two vertices are adjacent in the same part or the same partition. So let's draw this out. I think that's everything there. No. I think that's, yeah. So clearly, if you look at these two sets, there's no vertices adjacent to each other here, unless I drew those in. So this is a complete graph, complete bipartite graph on three vertices. And there's actually a very interesting theorem. So it's proven, so it's a theorem presented by Polish mathematician, so it's Kuratowski's theorem. Basically says that a graph is planar if and only if it contains no subdivision of K5 or K3, or the complete bipartite graph on three vertices. So Kuratowski was this Polish mathematician who was famous for his contributions to a few different areas of mathematics, primarily in set theory, topology, measure theory, and this subject, and graph theory as well. So that Kuratowski's theorem, there was a few words that need to be explained, but it's not part of this proof. So like subdivision, and obviously you need to know what K33 is as well. But that's not important. That might pique your interest. So let's go over the proof. Let's not waste any more time. We've got all the essential elements here, the definitions of planarity, planar embedding, a few illustrative examples. We know what K5 kind of needs. We have the Jordan curve theorem stated. Let's go over the proof. So this is only one of many different approaches we can take to prove the non-planarity of the complete graph on 5 vertices. But I like this proof in particular, so that's the one I will proceed with. What we're going to do is prove using the method of contradiction. So we suppose for a contradiction that the complete graph on 5 vertices is planar. Because I want to prove that it is non-planar using the method of contradiction. So we suppose for a contradiction that K5 is a planar graph. So then what we want to do is let, let's say G, be a planar embedding. So if K5 is planar, there exists some planar embedding of K5. And let's give this graph G, this planar embedding G, well, let's label some vertices. So let's call them, so we need 5, let's call it. So with vertices, say V1, V2, V3, V4 up to V5. So now what we want to do is consider the cycle C equals V1, V2, V3, and back to V1. So we're not including V5 yet. So we have this cycle here. We know that this cycle exists since all vertices are adjacent to each other, right? So you just trace from the point V1, wherever it is on the plane, a cycle from V1 to V2 to V3, and then you go back to V1. So every, I guess, pair in this way is an edge, because we have the complete graph. Now, notice something about C. It's a cycle. It is also a simple closed curve, and you might be thinking about the Jordan curve theorem here, but we're not going to use it quite yet. So C is a simple closed curve. And I guess in a sense we'll have to use it, or this statement of the definition. So we have a simple closed curve. What does that mean? What does that imply? Let's draw something out. That's C. You have an interior and an exterior. So that's what you have. I think I did not mention what an interior, or officially what it is. I guess I could explain it now. So if you have this curve here, should have mentioned it in the Jordan curve theorem, but here you have this curve. You have those two disjoint arcwise connected open sets. This one on the outside, the exterior. This one on the inside of the curve C, we call the interior. So we can call those two open sets. So this one here, we could say is the interior of C, and this open set here is the exterior of C. So that's important to note. So yeah, C is a simple closed curve. So we have an interior of C and an exterior of C. They exist. So the vertex V4 must lie in either the interior of this cycle or the curve or the exterior. So it's in either one. So you have the curve lies either here or here. So we can say, let's choose one for the sake of our proof. So without loss of generality, let's assume that vertex V4 lives in the interior of the cycle. So we've got a lot of words here so far. Let's draw a diagram. So we can have, let's say V1 is over here. Let's say V2 is over here. And V3 out here. So we have our cycle, V1, V2, V3, back to V1. And because we assume that V4 lives in the interior, let's put it right here, V4. And because we have the complete graph, we have edges between V1 and V4, V3 and V4, and V2 and V4. Not a curve, let's make it straight. So this kind of looks like, or it is, a planar embedding of the complete graph on 4 vertices, right? So in a sense, what we want to do is extend this with an additional vertex, V5, and show that no planar embedding exists as soon as you introduce an additional vertex. So let's continue. So I guess we could have drawn these edges in interesting ways, but I just kind of made them straight and direct for the sake of a better illustration. So because we want to preserve the planarity of the graph G, those edges V1, V4, V2, V4, and V3, V4 all lie entirely within the interior of C, as you can see here in this diagram I've drawn. And we want to make the exception that their ends don't have to lie in the interior of C. Because really it doesn't matter, it doesn't make a substantial difference in the result of this proof. So what we want to do now is consider these cycles over here. And let's give them formal names. So let's C1 equal the cycle from V2 to V3 to V4 back to V2. C2 to be the cycle from V3 to V4 to V1 and back to V3. And this last cycle here, C3, to be the cycle from where should we start? V1, V2, V4, back to V1. So notice with the way I've constructed these three cycles that the vertex Vi is not, so say Ci, we have these cycles for I equals 1, 2, and 3. Say I equals 2. So in this case here, that vertex Vi, if I equals 2, then we have V2. It does not live in that cycle. It's just the way I've constructed it. So what we want to do now is, I guess, make some modifications of this graph here. Not the image, maybe just paste it. It's large. So let's draw out where our main cycle is. Our main cycle is going like this. And that's just C with no subscript, with no index. C, and then over here, if I zoom in, so let's identify where C1 is. C1, so the vertex V1 is not part of the cycle C1. So if we look here, we don't want this vertex to be part of the cycle. So the cycle in this graph here that does not include that vertex is this one here. So let's call this bit the interior of C1. And you do that with C2 and C3. You'll find that this is the interior of C2 because it kind of opposes that vertex. The interior of C3 opposes this vertex. So I'll just make it clear that Vi is part of the exterior of Ci for I is in 1, 2, 3. So all I'm saying here is that it's basically what I've already said, is that the vertex that corresponds with that cycle lives in the outside or the exterior of that particular cycle for all three cycles I've constructed here. Now, since the graph G is a planar embedding, because we've assumed that G, that K5 is planar, so G is the planar embedding. We've given it the name G. So since G is a planar embedding and Vi, V5, so this edge, so for I equals 1, 2, and 3, so consider that edge. It is an edge, it is part of the edge set because we have the complete graph on 5 vertices. So now we use the Jordan curve theorem, right? So if you can imagine where the 5th vertex should be placed on the plane. Remember, we want to preserve planarity. where can it be? So if you connect any of these vertices with V5, wherever V5 is, where should it live? Well, if we use the Jordan curve theorem, so let's just make it clear. By the Jordan curve theorem, that vertex V5 must be in the exterior of CI. For I is 1, 2, and 3. So let's think of an example here. So let's have a look at C2, which is that cycle there. Now V2, V5, so that edge connecting the vertices V2 and V5, V2 and wherever V5 is, maybe here. Well, this is in the exterior of this cycle, right? And because V2, V5 is part of the edge set, it cannot, or it must remain in the exterior of that cycle. And that's basically what I've said. And if you think about that in terms of the other vertices and the other cycles, V1, V2, V3, you'll notice that that V5 must live in the exterior of the cycle, of that corresponding cycle for these cases here. Right, so because that is the case for I equals 1, 2, and 3, so it must live in the exterior of here, here, and here. Well, the combination, I guess, in a sense, of these three cycles make up the cycle that I've drawn in pink there. So therefore, hence V5 must live in the exterior of the entire cycle. Right? Because the Jordan curve theorem says that we have two arc-wise connected disjoint open sets, right? So if we start in the exterior, we must remain in the exterior. Now let's look at this diagram here. I'm trying to make my point clear. So let's say that's V5 here. Right? It lives out there. And let's try to connect all the vertices, say V1 and V5, V2 and V5, V3 and V5. Now, because those edges exist, may not have to look like that exactly, but because there's an edge between those vertices, when you attempt to draw an edge from V4, this middle vertex here, out to V5, you cannot do it. You're trapped here, that's an edge crossing. You're trapped here, edge crossing, and obviously there's an edge crossing over here. All right, so you cannot leave the cycle without crossing the edge or the curve. But you find the graph is still planar, or a planar embedding at the point right now as I've drawn it. Right? There's no edge crossings yet. Even when you connect V1 to V5, V2 to V5, and V3 to V5. But it remains to connect one more pair of vertices, namely the vertices v4 and v5. Because of our construction, we've forced v4 to have to edge cross to get to v5. So v4, v5 must cross curve C, or the cycle, because v4 was in the interior of C, v5 is in the exterior of C, right? We can't have that. So we have a contradiction. There's no way you can make that connection without an edge crossing. And it's a contradiction because you cannot have a planar embedding because we have an edge crossing. So yeah, to construct K5, we just had to make that additional edge. We couldn't make that. Based off the way I've proved this, I've shown that K5 is not planar.